Okay, hello. Welcome back to another lecture. Here we have chapter 11. So, just to kind of recap where we've been recently, right? We talked about molecules, we talked about bonding, we've talked about reactions. Now we're going to kind of take another step, more of a lateral step, right? We've been building sort of up that tree for a long time. We're going to take a lateral move over to gases, because we've done a lot of talking about solids and liquids. Have you ever wondered how long is too long when making long straws for drinking soda? You've ever done that before? You take a bunch of straws and link them together. How far can you go? Well, it turns out there is a limit to how high you can go. Sucking on a straw removes some of the molecules from inside the straw and creates a pressure difference between the inside and the outside of the straw. The soda is then pushed up the straw by molecules in the atmosphere. So if the straw had a perfect seal and rigid walls, and there was a perfect vacuum inside of the straw, a straw longer than about 10.3 meters or 34 feet would not work. Why is this? So if we draw, an expertly drawn cup, let's make our straw, and then let's fill this in with water, right? So I got all this water, and we're going to start sucking, and we remove all of the air out of the straw so that the level of the liquid goes up. What's happening is, by removing the air above in the straw, and I kind of stuck myself a little too high up here, you're almost getting like a seesaw effect. So when you're pulling the air out of that straw, the atmosphere is pushing down on this water, and that is what causes the water to come in and go up the straw. But when you get to about 10.3 meters, the force of the atmosphere pushing in and up the straw is equivalent to the amount of mass or the weight of the water inside the straw. And so you can't push any higher because there's literally no more force from the atmosphere to push the water higher up the straw. So we're talking about the pressure then. Pressure is the force exerted per unit area by gas molecules as they collide with surfaces. On Earth at sea level, the gas molecules in our atmosphere exert an average pressure of 101,325 Newton meters, or about 14 pounds per square inch. So you can imagine if you had a straw that was 1 square inch, and then that straw extended up, the maximum amount of water that you could put into this straw, that you could suck up into this straw, would weigh 14.7 pounds. Because that is the amount of force that's being pushed down. So it's pushing down with 14.7 pounds of force. If you remove all of the air up here, you can only push up 14.7 pounds of water in a square inch. Right? So that changes for the height that the water can go, changes depending on the size of the area of the straw. So a straw in a glass of orange soda has equal pressure inside and outside the straw, right on the left here. So the liquid levels inside and outside stay the same, or are the same. When you suck on that straw, the pressure inside the straw is lowered, but the pressure on the surface of the liquid outside the straw is greater, so that pushes up, and it pushes the liquid up into the straw. Even with a perfect vacuum, atmospheric pressure can only push orange soda to a total height of 10 meters, right? We talked about that. Basically the same as water. A column water or soda, 10.3 meters high, exerts the same pressure downwards. So this is pushing downwards with 14.7 pounds. And that's your maximum height. The soda would rise until the pressure exerted by its weight equals the pressure exerted by the molecules in our atmosphere. Even with a perfect vacuum. And that's actually the reason that trees have a limited height. They can't get taller infinitely. They can only get as tall as the pressure will allow them to suck water up into the top of the tree. Now, the theory behind how gases behave is called kinetic molecular theory, and it's a model for understanding the behavior of gases. This model predicts the correct behavior for most gases under many conditions. But like other models, the kinetic molecular theory is not perfect and breaks down under certain conditions. And for this class, we're going to be focusing on those conditions where it works well, and we will talk very briefly about where it doesn't work well, because it helps to understand when it does. So these are the rules of kinetic molecular theory. Gases are a collection of particles in constant motion. There's no attractions or repulsions between these molecules or atoms of gas. There's a lot of space between the particles compared to the size of the particles themselves. The speed of the particles increases with increasing temperature. Kinetic molecular theory is consistent with our observed properties of gases. Right, so gases are compressible. Why are gases compressible? Because there's so much space in between the atoms, we can condense that space. But in a liquid, we don't have any space between our atoms or molecules, so they cannot compress. There's no space to shrink. Gases assume the shape of their container. The molecules in a gas do not interact with each other, and the particles are in constant straight line motion. So if you have, let's say you're cooking, or your wife, or your partner, or your mom, or your dad, somebody's cooking in the kitchen, whoever it may be. They're cooking, they're using garlic. You can smell that, at some point in every part of the house. And that's because if a molecule has a straight line, or an atom or a particle of gas has a straight line to travel all the way down your hallway, they will bounce around and eventually they will, it's called diffuse into every space. So you can imagine if we had like a long hallway. So let me make this bigger. Like this, right? Well, let's say you're over here and the kitchen is out here. We're going to use red, right? So somebody's cooking out here. Some of these particles are going to be going out in every direction. And some of these particles will go here and they'll bounce until they reach you. And they will continue in straight lines until they come into contact with something solid, in which case they'll bounce off. Gases have very low densities in comparison with solids and liquids, right? There's so much empty space between the gas that those particles are spread out. And there's much, much less mass in a larger area, right? So we talk about density, it's mass per unit volume. So for gases, we have a very small mass, or we have a mass, but we have it in a very large volume. Pressure is a prediction of kinetic molecular theory. Because pressure is the result of the constant collisions between the particles in the gas and the surfaces around them. Because of pressure, we can drink it from straws, we can inflate basketballs, and move air in and out of our lungs. Variation in pressure in Earth's atmosphere creates wind and changes in pressure help predict weather, right? If there's a high pressure front, that usually means it's going to get warm. If there's a low pressure front, it's going to cool off. So the pressure exerted by a gas sample is defined as the force per unit area, right? And that is a function of how many particles, how many molecules or atoms are hitting that area constantly to produce that force. So, for example, the side of this container, we have 1, 2, 3 particles, 4 particles that are hitting it right now. But if we look at this container, there's 1, 2, 3, 4, 5. This one's probably going to get over there, 6. Right? So we have higher pressure. And there are a number of things that change this. One of them is the number of gas particles. So if you have more gas particles, you have more frequent collisions. Another one would be temperature. So if your particles are moving faster, they're hitting the walls harder and exerting more pressure. We experience pressure variations, mostly if you're driving up into the mountains, or if you're driving to high elevation, or if you come from high elevation down to low elevation. The difference in atmospheric pressure we can feel behind our eardrums, right? That's why you have to yawn or drink or chew something to relieve that pressure so that it doesn't cause pain. Airplanes also experience that, right, when airplanes take off. So the simplest unit of pressure is the atmosphere, and that is defined as the average pressure at sea level. The SI unit of pressure, however, is the Pascal, and it is defined as 1 Newton per square meter. The Pascal is a much smaller unit than atmospheres. There's 101,325 pascals for 1 atmosphere. Conversion factors. We also measure pressure historically as millimeters of mercury. So the millimeters of mercury comes from this glass tube filled with mercury, and then it's inverted without letting any air in, so that the end rests in a bath of mercury. The way you measure this then is from the surface of the mercury all the way up to the top of the mercury level, and which has a vacuum above it. So as the atmospheric pressure changes, if atmospheric pressure increases, then this level of mercury rises. You can also use inches of water. We'll show that conversion later. The reason mercury is so nice is because it's a very, very dense liquid. This column only has to be 30 inches high, or just over 30 inches high. If you have water, it's going to take a lot more water to get this level, or to create this effect, this vacuum. It would have to be over 10 meters tall. So we have this table here, very useful table. Units of pressure. You can find this one in your textbook. To save time, you should memorize these conversions at the very least. Going from 1 atmosphere to 760 millimeters of mercury. And that 760 millimeters of mercury is also 760 torr. These will be the most used or most used units. There are some other ones though. So we have inches of mercury. We have millimeters of mercury, which is exact. So millimeters of mercury and torr is exact. Are exact. So let's convert 1 atmosphere to torr. So 1 atmosphere, 1.25 atmospheres. And we know from here, so each of these is the average pressure at sea level. So you can create a conversion factor between any of these two. Or any two of these, I should say. So 1 atmosphere, if we have 1 atmosphere then, is 760. We want torr. Those are good ones to have memorized. 1.25 times 760 is 950 torr. Then if we want to do inches of mercury to millimeters of mercury, you know that 760 millimeters of mercury well, there's actually 2 ways that we can do this. So we could do 29.92 inches of mercury is equal to 760 millimeters of mercury. Could do it this way. Or what we could do instead is convert. I need to have my units here. 2.5 or sorry, 1 inch is 254, sorry, 25.4 millimeters. 30.15 times 25.4, 765.81. So if you wanted to do it the other way that I had written out before, we should get exactly the same answer. 30.15 times 760 divided by 29.92, and we get 765.84. So almost exactly the same answer. You can do that one either way. It's just inches and millimeters, and so you can convert those because it's the height of a column of mercury. So let's convert 173 inches of mercury into pounds per square inch. So pounds per square inch from our previous chart here, 14.7, 14.7 psi is the same as 760, oh, not 760 millimeters. Was it 29.92 inches of mercury. So we'll take 173 times 14.7 divided by 29.92. And we get almost exactly 85.00, because it's not quite psi, but you might have in a road bike tire. The pressure then, so we have this Boyle's law, right? It's a law, so it's going to tell us what happens when we do different things to gases. And Boyle's law is that the pressure of a gas sample depends in part on its volume. Most specifically, that if we have the constant temperature and a constant amount of gas, the pressure of a gas sample increases for a decrease in volume, and pressure decreases for an increase in volume. You can think of this if you've had like a bike pump. Actually, I think that's the next slide. If we have this bike pump, we're pushing down, and if you block the end of this, you can feel that pressure increase from the bike pump, because we're decreasing the volume by taking this chamber and making it smaller. So we're starting with a big chamber of air, and we're compressing it down into a smaller volume. The pressure increases. It gets harder to push down the bike pump as there's more pressure. Then on the upstroke, we're doing the opposite. So if you were to cover this, we have the same amount of air in here, and you pull up on it. You'd have to cover the one-way valve as well. What happens is we're increasing the volume inside of this bike pump, and it decreases the pressure. And because there's a decrease in pressure, that causes this one-way valve to open up and let air into the chamber. The relationships between gas properties are described by gas laws. So the relationship between volume and pressure was discovered by Robert Boyle. That's Boyle's law. Boyle's law assumes constant temperature and a constant number of gas particles. So this bike pump only has a constant number of gas particles if we plug this one-way valve and if we plug the end of the pump. We write Boyle's law like this. Then volume, and this means inversely, so volume is inversely proportional, well, this is saying volume is proportional to 1 over pressure. So it means that they're inversely proportional. So as we increase pressure, we decrease volume. And you can calculate, if we know the pressure and the volume, and we change one of those, we can determine the other. You'll see what I mean in a second, when we do some examples. So this is a barometer. Right? As we increase the pressure, our volume decreases. If we add more mercury to the other end, oops, thought I had the pointer. If we add mercury to this end, that increases this, or decreases this volume, because we're increasing the pressure pushing on that side. So you can see here this plotted out. We have the volume as our y-axis and pressure as our x-axis. And as we increase pressure, as we move to the right along pressure, this volume decreases. When plotted V versus P, so pressure as the X and volume as the Y, we get this curve. When we plot it V versus 1 over P, we get a straight line. That's one of the ways we identify if something has an inversely proportional relationship, is that you get a straight line when you plot volume versus the inverse of the pressure. Perfectly proportional. Kinetic molecular theory explains Boyle's law as well. Right? So if we have a scientific theory, that's why things happen. If we have a scientific law, that's what happens. So Boyle's law tells us what's going to happen if we change pressure or volume, but kinetic molecular theory backs that up by explaining what's going on. So if the volume decreases with the same number of gas particles, there will be more collisions at the walls of the container, leading to an increase in pressure. So we've taken these gas particles and we've decreased the amount of space that they have to move around in. So that means that they are traveling, they don't have to travel as far before encountering the walls of the container, and they have more collisions, which increases the pressure. One of the things, too, that I wanted to point out with these sort of pictures, these diagrams, is that the number of particles here is very deceptive. So the number of particles that's actually in a volume this size is billions and billions. It's an incredible number of particles, and that's why even though they're so small, they can exert such great pressure. So here's an example. We have a cylinder equipped with a movable piston. Has an applied pressure of 3 atmospheres and a volume of 5 liters. What is the volume of the cylinder if the pressure is decreased to 2 atmospheres? So first we should predict. We have decreasing pressure, so we should see an increase in volume. But what we need to determine is how much. So Boyle's law, as it's practically laid out, is P1V1 equals P2V2. The ones being here referring to our initial state, and the twos referring to our final state. So if we put in these numbers, pressure, 3.0 atmospheres, 5.0 liters for our volume, we're going to multiply those together, is equal to, we have a new pressure of 2.0 atmospheres, and we're solving for V2. So from here, it's just a little bit of algebra, a little bit of math. We're going to get 15 equals 2.0 atmospheres and V2. And this is now atmosphere liters. I should write that out. So 15 atmosphere liters. And then we're going to divide by atmospheres to get 7.5. And so atmospheres, right, we're dividing both sides by atmospheres. Atmospheres is going to cancel out. We're going to get 7.5 liters equals V2. And so our final volume then will be 7.5 liters after we decrease the pressure. That makes sense too. Since we're going from 5 liters up to 7.5 liters, because as we decrease pressure, we increase volume. Inversely proportional. Boyle's law explains also why ascending too quickly from a deep dive is dangerous. For every 10 meters of depth, a diver experiences an extra 1 atmosphere of pressure. Because of this extra pressure, really crushing the body of the diver, the pressure of this regulator on the scuba tank needs to increase its pressure to match. Because it's great differences in pressure that matter the most. If you come up too quickly before your regulator can adjust, now you've got 3 atmospheres of pressure in your lungs pushing out against the 1 atmosphere outside. So you've got essentially 30 pounds per square inch of force exploding your lungs. You can imagine that that would be painful and damaging, to say the least. So if we take our snorkeler has a syringe filled with 16 milliliters of air from the surface. so at atmospheric pressure. They take that syringe down to an unknown depth. The volume of the air in the syringe at that depth, at the new depth, right? So they've dove down. It's now 7.5 milliliters. What is the pressure at this depth? So let's take our P1V1 equals P2V2. And we're also given that if the pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? So we're going to find the pressure first. We're starting with 16 mils. The important thing to remember about Boyle's law, let me erase this, 1.0 atmospheres. The important thing to remember about Boyle's law and units is that the units on either side have to be the same. So if we're using atmospheres and milliliters, we need to be using atmospheres and milliliters on the other side. So now we've gone from a volume of 16 milliliters to 7.5 milliliters. And actually what I'm going to do, I'm going to rearrange this just a little bit. We're going to put pressure back behind our number there. So we're going to get 1 times 16, that gives us 16 milliliters, equals 7.5 milliliters, or sorry, 16 atmosphere milliliters. And then we're going to divide 16 by 7.5. And we're going to get 2.13 atmospheres is the new pressure at that depth. So how deep then did the diver go? Well, we're given 1 atmosphere for every 10 meters of depth. So now we can take our pressure that we found, atmospheres, and we can say 10 meters over 1 atmosphere. And we're going to get that the diver dove 21.3 meters. He better be careful to not come up too soon, or she. Who knows? They better be careful when they come up to the surface that they don't explode their lungs. So again, right, it's very important to understand how to manipulate units. It can make these problems a lot easier. So we'll move on then to Charles' law. Now Charles' law deals with volume and temperature. So why does hot air rise? Well, when we heat a gas, it increases the volume as long as we're at a constant pressure. So the mass doesn't change. It's the same amount of number of particles, but the volume has increased. So we've decreased the density. So you may know that things float in water because they are less dense than water. Similarly, a lower density gas, or things that are of a lower density than air, will float in air. So these hot gases have a buoyancy in air that you can use to fly a hot air balloon. Volume increases with temperature. As we heat things up, speed of those particles goes faster and it increases the volume. Volume also decreases with lowered temperature. And according to, if we're using a Kelvin scale, here this is in Celsius, but at negative 273 degrees C, the extrapolation of this line predicts that gas should have 0 volume. And we cannot go below 0 volume. And so we call this point absolute zero. And that's why it's negative 273 degrees C is equal to 0 Kelvin. Not degrees Kelvin. I guess I should do this so you don't think it's okay. It was J.A.C. Charles, a French mathematician and physicist, who quantified the relationship between the volume of a gas and its temperature. Charles' law, so Boyle's law, we're assuming that we have a constant temperature and a constant number of moles. Charles' law assumes that we have a constant pressure and a constant amount of gas. And for Charles' law, the volume of a gas and its Kelvin temperature, this is critically important, its Kelvin temperature are directly proportional. So if we increase volume, then we also increase temperature. And that works out to this equation. V1 over T2 equals V2 over T2. So if we take the temperature of a gas sample and we double it, the volume doubles. But the temperatures must be expressed in Kelvin, because if we double 2 degrees C, that's very different. Doubling this goes from 2 degrees C to 4 degrees C. But if we were to do this in Kelvin, right, 273 Kelvin is 2 degrees, or is 0 degrees Celsius. So this would be 275 degrees, sorry, not degrees, Kelvin. Kelvin would double to 550 Kelvin. So you have to use Kelvin, because Kelvin is the only time where the temperature scale, or the y-intercept, is 0, as we saw in our previous one. So kinetic molecular theory also explains this as well. That if the temperature of a gas sample is increased, the particles move faster. And for pressure to remain constant, the volume must increase. Because that's one of our stipulations with Charles' law, is that it's constant pressure. So Charles' law, if we take ice water, if we take a balloon and we put it into ice water, it shrinks. And then if we take that same balloon even and throw it into boiling water, then that balloon is going to expand. I will post in the description for this video, I will post a link to a cool demonstration where they take a balloon and they stick it in liquid nitrogen. Cannot remember exactly the temperature of liquid nitrogen, but it's very, very cold. So let's use this then and do some maths with it. A sample of gas had a volume of 2.8 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases to 2.57 liters. What was its initial temperature? In kelvins and in Celsius. So, we have our equation. Actually, I think it's V1 over T1, isn't it? V1 over T1. Doesn't really matter. V1 over T1 equals V2 over T2. R2D2. A sample of gas has a volume of 2.8 liters at an unknown temperature. So we're going to do 2.8 liters. Temperature unknown. You can use these either way. I'm going to shift that over. And so if you have your ending conditions, you can get one of your starting conditions. And if you have your starting conditions, you can get one of your ending conditions. But you always have to have 3 of the pieces to solve. So its volume decreased to 2.57 liters. 2.57 liters. From a temperature, it decreased to 2.57 liters at 0 degrees C. Now, I know I was just saying that you have to use degrees Celsius. Actually, let me think about this. Let's try doing this with degrees Celsius. Let's see what happens. Okay? So we have 0 degrees C. Oh, immediately there's a problem, right? If we do this with 0 degrees C, now we're dividing by 0. And we can't do that. So instead we have to convert to Kelvin. We'll use the more accurate 273.15. Kelvin. So we take 2.57 divided by 273.15, and we're going to multiply that by 2.8. So 2.8 liters. Whoops. 0.0263 uh did I goof here? It's like I will be editing this video. Oh, yeah, I did goof. 2.57 divided by 273.15. And then we're going to take 2.8 divided by whatever that answer was. Wow. Okay. 297.5, oh, not 59, 60 Kelvin is equal to T1. Did a bad job of the algebra there. So then to convert that, we subtract 273.15 to get 24.4 degrees C. And that gives us our temperature in Kelvin and in Celsius. So if you use Celsius, you're going to run into problems like this. Because it is not proportional to degrees Celsius, it is only proportional in kelvins. Another problem then. Gas in a cylinder with a movable piston, classic. Gotta love the gas in the cylinder with a movable piston. Has an initial volume of 88.2 milliliters, excuse me. It's heated. We go from 36, a little flame. We're gonna go from 36 degrees C to 155 degrees C. So you should know by now our first step is to do 273.15 plus 36 to get 309.15, and 155 plus 273.15 Kelvin, of course, 428.15 Kelvin. So our initial volume is 88.2 milliliters. It's 309.15 Kelvin as our start. Our new volume is unknown. And our new temperature will be 428.15 Kelvin. So we'll just do 88.2 divided by 309.15 times 428.15 for 122.15 milliliters. So again, just like we had before, the volume unit has to be the same as what we start with. So if we use milliliters here, our answer is going to be in milliliters. And that is because we're multiplying this K up here, so the K for Kelvin is going to cancel. We can then take Boyle's law, and we can take Charles' law, and we combine them together for situations when two variables change at once. So the amount of gas in this equation, the amount of gas is constant, and the temperature is in kelvins, because the temperature is in kelvins for Charles' law. The pressure and volume units don't matter as long as they're the same on either side. So if we have a sample of gas with an initial volume, I'm going to write this, P1V1 over T1 is equal to P2V2 over T2. I think I already made a C3PO joke. No, R2D2. Okay. Pressure here. Let's just double check. We have 34 degrees C. And we have 85 degrees C. And so we're going to need to convert those. 307.15 Kelvin. Should just, I can't do it on this calculator. I was going to say I should just save a variable. Oh, I think I can. 273.1, whoops, 0.15. So I don't have to keep typing it. 358.15. So we've converted our temperatures and our, we're in milliliters, but we're going from milliliters to milliliters. We want to know what is the final pressure in millimeters of mercury. So that's good, millimeters of mercury. We're starting with millimeters of mercury. So we can just fill in these blanks. 735 times 158 mils. Sorry, I should, units. Sorry, just looking at the top of my head, but I guess you do that a lot. So now we're going to do 307.15 Kelvin. And then we're going to have a new pressure, which is what we're looking for in millimeters of mercury, 108 milliliters. We're going to divide by, not 85, but 358.15 Kelvin. So on our left side, we can just take 735 plus 158 and divide by 307.15. And then we will, I'm going to do it this way. I'm going to multiply by 358.15, then divide by 108. If you need me to go over those, the way that I'm converting those, or the algebra, we can do that. Shoot me a message. 9.64. Again, we're looking for millimeters of mercury. And as you can see here, I've canceled out all the units, because Kelvin goes on top, milliliters is going to go on bottom, and we're left with millimeter of mercury for our new pressure. So you can see we've got a couple different things going on here. We're compressing this to a smaller volume, and we're heating it. So I may have done my math wrong again, because that seems awful small. Oh, I did 735 plus 158. 735. See, this is what I'm asking you guys to do on your homeworks, is to look at your answers and see if they make sense. Because 735 times 158 divided by 307.15 times 358.15 divided by 108 should be, yes, thank you, that makes a lot more sense. Right, so in this kind of scenario, we've decreased the volume, so our pressure should go up, and we've increased the temperature, so our pressure should also go up from that. So we should get a huge pressure here, and we do. 1,253. I guess we're only working with 3 sig figs here, so let's do 1.25 times 10 to the 3 millimeters of mercury. So we went from 753 to 1,250. 1,250. Another combined gas law problem. I'll write this up here. P1, V1, T1, P2, V2, T2. As long as you can remember this equation, these problems are generally fairly simple. You need to remember the equation, and remember to convert from degrees C to Kelvin, and then perhaps back again if that's what the answer is looking for. That is not the case here. We are going to do... Okay, so let's read the problem. A balloon has a volume of 3.7 liters at a pressure of 1.1 atmospheres and a temperature of 30 degrees Celsius. Right, so we'll have to convert that. If the balloon is submerged in water to a depth where the pressure is 4.7 atmospheres and the temperature is 15 degrees C, what will its volume be? Assume that any changes in pressure caused by the skin of the balloon are negligible. Because if you're really thinking about it, if the rubber of the balloon is cooling, then it's probably less stretchy, and so it'll pull in on the gas inside, but we're not considering that. We've been told to ignore it. So, from there, we're going from 30 degrees C to 15 degrees C. So we're going to do 30 plus 273.15 to get 303.15 Kelvin, not degrees Kelvin. 15 plus 273.15, 288.15 Kelvin. So we've got then 3.7 liters times 1.1 atmospheres over 303.15 Kelvin. And that is going to be equal to, we're looking for temperature. We're looking for volume. So we'll put our pressure here, 4.7 atmospheres. So they've descended about 30 meters. Good golly. 4.7 atmospheres, and we want to know the volume. And our temperature is decreased to 88.15 Kelvin. So before we go through and we type out all this math, and actually maybe as I am typing the math, I'll talk about this. We should be looking at what we expect to happen to this volume of gas. We are increasing pressure. So as we increase pressure, we're going to decrease volume. And as we decrease temperature, we also decrease volume. Increasing pressure, decrease volume. Decreasing temperature, decrease volume. So again, we have this sort of dual effect, and so we should expect this volume to get very small. Oh, I kind of switched these back and forth. Don't be confused. That's why you put units. Sorry, so where was I? I'm multiplying by 288, and I'm going to divide by 4.7. So our volume then has gone from 3.7 liters down to 0.82 liters. Very much just plug and chug kind of problems. Nothing crazy. Avogadro's law takes this final relationship that we haven't talked about yet, and that is the relationship between the amount of gas and its volume. And what we find is that as we increase the number of moles, we increase the volume. This should be fairly intuitive once we think about it and put it into everyday terms. So this relationship was first stated by Amadeo Avogadro. It assumes constant temperature and pressure. So we've got a constant temperature, constant pressure. So we're in an enclosed space. Sorry, not an enclosed space. We're not in an enclosed space. We're in something like a balloon. So Avogadro's law is that the volume of gas and the amount of gas in moles are directly proportional. The amount of gas in moles, another important unit. So when we do these kind of problems, we need number of moles here to, or N here to be a number of moles, not in grams. These are proportional. Again, a balloon. If you have this balloon, when you blow into the balloon, you're adding moles of gas. You're adding molecules into the balloon at a constant pressure so that it increases its volume. So if we have a 4.8 liter sample of helium, contains 0.22 moles. I should write this up here, right? V1N1 is V2N2. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? So we have our V1 and our N1. Now we're going to enter in our V2, 6.4 liters, and our N2 we leave down here, because we're solving for N2. So we're going to take 4.8 divided by 0.22. We're going to take then 6.4 divided by the answer that we got from 4.8 divided by 0.22. And we're going to get 0.29 moles of helium at our final volume. So I did this division, and then I divided both sides by this on the left side, took this, clicked the wrong thing, took this, I took 6.4, divided by the product of this, then I multiplied n up over to the left side. So we do in fact see an increase in moles, which is what we're looking for, and what we would expect. The question though, and this is how these sort of questions get tricky, how many additional moles of helium gas? So we're not quite done yet. We need to do 0.29 moles minus 0.22 moles, and we find that we're adding 0.07 moles of helium. It's the additional moles of helium that'll get you. Now let's say we have a chemical reaction occurring in a cylinder equipped with a movable piston that produces 0.58 moles of a gaseous product. Produces 0.58 moles. That's our N2. If the cylinder contained 0.11 moles, oh, we have N1, 0.11 moles of gas before the reaction and had an initial volume, oh, V1, thank you very much, liters, what was the volume of the reaction? After the reaction, excuse me. Surprised that you can't see that. There's like a hair in front of the camera. Okay. So we've got N2, N1, and V1. Now you can see that we've gone from 0.11 moles to 0.58 moles. So we've increased our number of moles by a lot. So we should see a proportionally great increase in our volume. I would expect to see about 5 times increase. So we're looking for around 10 liters, right? Because we've taken our N1, multiplied it by 5, roughly, to get our final. So 2.1 liters over 0.11 moles is equal to V2 over 0.58 moles. So we're just going to do 2.1 divided by 0.11 times 0.58. Oh, and would you just believe it? 11 is what we're going to get for our sig figs too. Is going to be V2. Right? We have 2 sig figs. So 11 liters. Just about 10 liters. So you can kind of predict in some of these cases how many that you're going to get for these simpler problems. How many of whatever unit you're going to get. Especially when it's something as easy as a 5 times increase. It's a directly proportional increase. So just like the Power Rangers, if you bring them all together, you can create a super gas law. And what we call the ideal gas law. Combined to defeat, I don't remember who the bad guy in Power Rangers was. But the ideal gas law constant, you'll notice there's a little extra bonus thrown in here. That R is this 0.0821 liters, atmospheres, mole, Kelvin. This is why I tell you to write your units all the time. So I keep mentioning it in the videos, at least, if you listen to that. Each of the quantities in the ideal gas law must be expressed in the units within R. And one of the easiest ways to make sure that you're doing that is to write them out when you're writing down your question. And when you're filling out and doing your math, carry those units along. You know, it'll put a couple extra miles of travel onto your pen or your stylus, depending on what you're using. But it's worth it for those extra points it'll save you. So we're using pressure in atmospheres, volume in liters, amount of gas in moles, and temperature in kelvins. So we've carried over these moles and Kelvin from our previous 2 gas laws of Avogadro and Charles' law. These are some of the relationships. So we can take these things, and if you hold some of these quantities constant, you end up with We didn't talk about Gay-Lussac's law, but you end up with the simple gas laws, just under certain constant conditions. So let's take now and use our new Megazord ideal gas law and calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 kelvins. All so graciously provided in the units we require. So our ideal gas law, sometimes called PIV-NERT, PV equals nRT, and we can just fill these quantities in. So we're looking for, we have pressure, 1.37 atmospheres, and we're looking for volume. N is 0.854 moles. R, we're given R. R is 0.0821 atmospheres, moles. Wait. Liters atmospheres per mole Kelvin. Wait a second. Liters atmospheres per mole Kelvin. And we also have temperature. Temperature is given in the units we require. So if you always write out your units, you can always go back and check that we do in fact have atmospheres for atmospheres. We want our answer in just volume, so liters. We have moles for moles, and we have Kelvin for the Kelvin. So those will all cancel out to give us the units that we're looking for, which are liters, or a unit of volume. So then 8.5 or 0.854 times 0.0821 times 315, then all of that divided by 1.37. Our volume under these conditions is 16. Check how many significant figures we have, 16.1 liters. Very, very much plug and chug. If we have an 8.5 liter tire, again, right, PV, PIV-NERT, PV equals nRT, PIV-NERT. We have 8.5 liters. Oh, we want to know the pressure in the tire. So P, 0.55 moles, 0.0821 atmosphere liters per mole Kelvin, and 306 Kelvin. So again, plug and chug. 0.55 times 0.0821 times 306 divided by 8.5. And you can see how, too, it's very, very useful to know the SI units. We're going to be using them non-stop, and especially in these gas law problems where the units matter so much. This will be in atmospheres. Where the units matter so much, because if you use the wrong units, you're going to get very much the wrong answer. 306 Kelvin minus 273.15 is 32.85 degrees Celsius. If you use this and multiply by 32 instead of 306, you're going to be off by almost a factor of 10. And so your answer is going to be 0.16 atmospheres, at least in this case, instead of 1.6. So it's important to know these SI units and be able to recognize them at a glance. Another. So again, PV equals nRT. How much volume? Okay, we're looking for volume. Does 0.556 moles of gas occupy when its pressure is 715? 715 millimeters of mercury. So we're going to have to take that. We'll nix that out of there. We'll use our conversion factors, which you should memorize. 715 millimeters of mercury. 1 atmosphere equal to 760 millimeters of mercury equal to 760 torr. So millimeters of mercury, 1 atmosphere, 760 millimeters of mercury. So then 715 divided by 760 is 0.941. We really do want to use the exact number here. Again, you don't round until you get to the end of the problem. Otherwise, you end up with rounding errors. Now we just need our temperature, and also we need to convert it. So we're going to add 273.15 to get 331.15. 331. Excuse me. Come here. 15 Kelvin. 0.556 times 0.0821 times 331.15 divided by 0.941. And our answer is 16.0 liters. Remember, even though this lecture is recorded and I will be decently busy, I am still available to answer your questions. So send them on over. We can use the ideal gas law with mass in measurements. I think there's a typo here. We can use the ideal gas law with mass measurements to calculate the molar mass of a gas. As if that needed to rhyme. A sample of gas, has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees C and a pressure of 886 torr. Find the molar mass of the gas. Several things here. Our units for R: atmospheres, liters, mole, Kelvin. Right? What are our units here in this problem? Mass will be important later. We'll deal with it. But we have volume in milliliters, we have temperature in degrees C, and we have pressure in torr. The problem can't even start yet. We've got too much other stuff to do. Volume, however, to our benefit, volume is easy to convert. Just divide by 1,000. Do that one in my head. 0.224 liters. Put this in here, right? PV equals nRT. We've already written N in. Let's do temperature next. 55 plus 273.15. 328.15 Kelvin. And then we just need pressure. And we're given in torr. So again, 1 atmosphere is equal to 760 torr. So we divide 886. Torr equals, or I guess multiply by 1 atmosphere over 760 torr. So 886 divided by 760. And then I'm just going to get on with the rest of the problem. That's 1.1657. Actually, I should, just for trying to come back and get the significant figures later, atmospheres. So we're going to multiply that by 0.224. And then we're going to divide by 0.0821 divided by 328.15. 0.00969 moles of whatever our mystery gas is. We want to know the molecular weight. the molecular mass, the molar mass of the gas. So this is just the molar mass of the gas, because we don't know if it's a single molecule or not. We take our moles, we take our grams, which again, we have milligrams. So 0.0388 grams divided by 0.00969 moles. 0.0388 divided by 0.00969, and we get 4 grams per mole as our molecular weight, molecular mass, or molar mass, excuse me. Goodness gracious. If you want to fight me about sig figs, 4.0. Right, so let's find another molar mass. We have a mass measurement. We're given a volume, this time graciously in liters, but we are also given 88 degrees C in degree C, 88 plus 273.15, 361.15 Kelvin, 976 divided by 760, 1.2842. Our mass again is given as milligrams, so this is going to be 0.827 grams. Now it's just plug and chug. Right, PV equals nRT. So P, 1.2842 atmospheres times 0.270 liters. We're looking for moles. And then we also want 0.0821 atmospheres liters per mole Kelvin times our temperature, 361.15 Kelvin. Plug and chug. 0.270. All right, so 1.2842 times 0.270 divided by 0.0821 divided by 361.15. We've got 0.01169 moles, right? More sig figs than we should have, but that's because we're not done yet. And we're going to take 0.827, which is our mass, because molar mass is in grams per mole, divided by that, and we're going to get 70.7 grams per mole. So we're talking about ideal gases here, and ideal gas conditions are this: high temperature, low pressure. We want our particle size to be small compared to the space between particles, and the interaction between particles are insignificant. We can get out of those ideal conditions and into non-ideal conditions if we lower the temperature, increase the pressure, because if we lower temperature, increase pressure, our molecules aren't moving as fast. There's a high pressure, so there's a lot of molecules near each other, and so that proximity combined with a lower speed means that we get some intermolecular interactions. And if that particle size then is also significant compared to the space between particles, and the interactions between particles are significant, we enter these realms of non-ideality. And in those situations, the particles do not behave according to our ideal gas law, which is for ideal gases. That was just a note on that. Now, according to kinetic molecular theory, each of the components in a gas mixture acts independently of the others. So if we have a lot of different types of gas, they're acting independently from each other. The pressure due to any individual component in a gas mixture is called the partial pressure of the component. The partial pressure of any component is that component's fractional composition times the total pressure of the mixture. Fractional composition being some percentage, right? So anywhere from 0 to 1. And so that could be something like 0.769 or 0.422. So if we were to convert these two percentages, they'd be 76.9% and 42.2%. So you can just take the percentage. Well, you're not going to use the percentage. You're going to use this fractional composition, which can be expressed easily in a percentage. You're going to multiply that by the total pressure to get the pressure of individual components. For example, the air in our atmosphere is a mixture containing 78% nitrogen, actually, 21% oxygen, and 0.9% argon, and 0.04% carbon dioxide, and a few other gases in smaller amounts, including helium. The nitrogen molecules in air exert a certain pressure, and it's 78% of the total pressure. That is independent of the presence of other gases in the mixture. The oxygen molecules in the air exert a certain pressure, which is 21% of the total pressure. It is also independent of the presence of other gases in the mixture, right? So we would express these as 0.21, 0.78. An optimist may see the glass as half full, and a pessimist may see the glass as half empty. But as a chemist, the glass is completely full. It's just 50% water, 39% nitrogen, 10.5% oxygen, 0.44% argon, and 0.06% CO2. The glass is always full. So if we have partial pressures here, the fractional composition is the percent composition divided by 100. So for P total here is 1, and we have 80% helium. That means we have 0.8 atmospheres of helium. And that means we also have 20% neon. We have 0.2% atmospheres of neon pressure. So let's say we have a gas mixture containing 64% methane and 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component? Cool. So we have 1.44 atmospheres times, for methane, 0.64. Right, because that's the fractional component of methane. And then we'll just do 1.44 atmospheres times 0.36. So these come from here. Oops. Okay, and we just multiply. 1.44 times 0.64, 0.92 atmospheres of methane, 0.36 times 1.44 will give us 0.52 atmospheres of ethane. And what you'll notice is that if we add these together, we get 1.44. So we've just taken that total pressure and we've said that the amount of pressure being exerted by any gas or molecule that makes up the gases is equal to that proportion of the total pressure. Dalton's law of partial pressures is this, that the sum of the partial pressures of each component in a gas mixture must be equal to the total, right? So that's what we saw in the previous slide here. The sum of these two gases is equal to the total pressure of the mixture. So P total is our total, and then P, A, B, and C, those are the partial pressures of the components, so on and so forth. So let's say we have a sample of hydrogen gas mixed with water vapor. The mixture has a total pressure of 754 torr, and the water vapor has a partial pressure of 24 torr. What is the partial pressure of the hydrogen? So if we have 745 torr total, that is going to be equal to the pressure of our hydrogen plus the pressure of our water vapor, which is 24 torr. So you can see that we just take 745 minus 24. We have 721 torr equals the pressure of hydrogen. Our lungs are tuned, at least for those of us living at sea level, they're tuned to perform an oxygen partial pressure of 0.21 atmospheres. This is why you can get lightheaded at high altitudes. If you go high enough, you can get hypoxia. Hypo, meaning too little, and oxia, meaning oxygen, or lack of oxygen. So we have too little oxygen. Severe hypoxia at partial pressures, or at partial pressures less than 0.1 atmospheres, may result in death. You can also have the opposite and have oxygen toxicity. So if the partial pressure of oxygen gets too high, you can experience twitching, tunnel vision, and convulsions. It may occur if you're breathing pressurized oxygen, such as while scuba diving. So if you turn up the pressure on your regulator too quickly before you dive deep enough, you'll get too much oxygen, and you can get oxygen toxicity. Too much of a good thing is a bad thing. Pressurized air also has an increased partial pressure of nitrogen. You can actually get what's called nitrogen narcosis, or the rapture of the deep. Apparently it feels similar to being tipsy. Deep sea divers beyond 50 meters will use specialized mixtures of gases, such as heliox, which is a mixture of helium and oxygen, so that they don't get this nitrogen narcosis, because helium doesn't have the same effect. So say we have a diver breathing heliox with an oxygen composition of 5%. He wants to adjust the total pressure so that the PO2 is equal to 0.21 atmospheres. What must the total pressure be? So he's breathing heliox with an oxygen composition of 5%. He wants to adjust the total pressure so that he gets 0.21% atmospheres. So the total pressure then, if this 0.21 atmospheres equals 5%, 0.05, then the total pressure if we want that to be 5%, let me see. I'm trying to figure out how to write this up so that it makes sense to you. If we take our total pressure, let's call this P total, and we multiply it by 0.05 to get our partial, because that's what we want the oxygen level to be. That will give us a 0.21 atmospheres O2. Does that make sense? So let's find the answer, and I can show you maybe a little bit more why this makes sense. So our P total then is equal to, right, we'll just divide 0.21 divided by 0.05. And this is another one of those examples where if you know what you're looking for, you can kind of predict what your answer is going to be. If 5% of our mixture is 0.21 atmospheres, then our total has to be 95, well, it doesn't quite work out to 95% greater, but the other 95% is going to be much more. So our P total has to be 4.2 atmospheres. Right? So this is how I think about this math in my head. If we were to take 4.2 times 0.05, that will equal, and if this is our percent O2, that will equal 0.21. So if we don't know what the initial pressure is, what our P total is, we just replace that. Whoops. And we know what our final oxygen is going to be, or what we want it to be, after we get 5%. So we take this, we take 5% of it, it should equal this. So now we can just solve this equation for pressure total. Sometimes we do this where we collect a gas over water. So you take your beaker and you fill it up. So you essentially have a vacuum over that. But when we collect a gas through water, the water molecules become mixed with the gas molecules. So you get a little bit of water vapor. And the final, the pressure of the water vapor in the final mixture is the vapor pressure of the water, which is dependent on the temperature at which the gas is collected. So let's say we collect hydrogen gas over water at a total pressure of 758 millimeters of mercury at a temperature of 25 degrees C. What is the partial pressure of hydrogen gas? So this is our P total. It's going to be 758 millimeters of mercury. And then to get our vapor pressure of water, we just have to look over here at 25 degrees C. And we're going to see that it's 23.8. So we know that P total is equal to, in this case, we're collecting hydrogen, so H2, actually I should say millimeters of mercury of H2, plus our pressure of water, 23.8 millimeters of mercury H2O. So then we can just replace our P total with 758 millimeters of mercury. We just say 758 minus 23.8. And we get 734 millimeters mercury hydrogen as our answer. So we just subtract out the partial pressure of the water there. In reactions involving gaseous products, reactants or products, the amount of gas is often specified in terms of its volume at a given temperature and pressure. We use the ideal gas law to convert pressure, volume, and temperature to moles. Then we use the stoichiometric coefficients to convert other quantities in the reaction. So if we're given a pressure, volume, and temperature of our gas, that will tell us how many moles we have, and then we can use that number of moles along with our reaction to get other quantities in the reaction. So in this reaction we have 4.58 liters of oxygen, 745 millimeters of mercury, 308 Kelvin. How many grams of silver oxide decomposed? Okay, so we're given this quantity, basically. We got to convert millimeters of mercury to atmospheres, so it's 745 divided by 760. Get 0.980 atmospheres. And now it's just PV equals nRT. We want to know how many grams, so we'll get there. We have 0.980 times, units, times 4.58 liters equals N times our R, 0.0821, atmosphere, liter, mole, Kelvin. And then, fortunately, we're given our temperature in Kelvin as 308. So, 0.980 times 4.58 divided by 0.0821 divided by 308. We have 0.177 moles of O2. For every mole of O2, we had to decompose 2 moles of silver 2 oxide. And so we take our number of moles there and multiply it by 2. And then we want to convert. So where am I working at here? Let's get the other periodic table. Cool. This periodic table go away. That extra white background go away. Silver is 107.87. Times 2, and then 16 times 1. Since we're converting from moles to grams, we want to multiply by the molecular mass. 107.87 times, whoa, pressed something weird there, 107.87 times 2 plus 16. And so we end up with 82.3 grams of silver 2 oxide, silver oxide, decomposed. A couple more slides here. There's a very convenient quality about gases, and that is that at standard temperature and pressure, STP being 273 Kelvin, 1 atmosphere, 1 mole of gas. Oops. And so let's calculate the volume of 1 mole of gas. That's what we're doing here. Standard temperature and pressure, 273 Kelvin, 1 atmosphere. So we're calculating the volume. We have 1 atmosphere, and we have a volume that we're looking for. We have 1 mole of gas times 0.0821 atmospheres liters per mole Kelvin, and we have 273 Kelvin. A lot of ones there, so all we have to do really is multiply 0.0821 times 273, and what we get is that volume of 1 mole of gas at STP is equal to 22.4 liters. This is true for any ideal gas, and most gases are going to be ideal at standard temperature and pressure. So this is a very, very convenient conversion factor, and definitely something that you should memorize. And it's the same for any gas, right? So for helium, for xenon, for oxygen, I guess you couldn't do like a metal as a gas because that would take a temperature that wasn't at STP. But at STP, every gas is 1 liter, or is 1 mole at 22.4 liters. Okay, so how many liters of oxygen at STP are required to form 10.5 grams of water? Okay, so 10.5 grams of water. Again, whenever we compare our 2 molecules or 2 atoms or whatever, got to go to moles first. Moles is like the grand unifier. That's like the bridge. That's like the central hub. We're always passing through there to go everywhere else. So we're going to take grams. We have 18 grams of H2O per 1 mole H2O. So 10.5 divided by 18 gives us 0.583 moles. And we have 22.4 liters per 1 mole. So we just multiply by 22.4, and we get 13.1 liters. Oh, sorry. Did you do that right? Oh, oxygen. I goofed. So we have 0.583 liter, or 58 moles of moles of water for every 2 moles H2O, we're going to get 1 mole O2. So we take this answer divided by 2, and it's actually 6.53 liters O2. So very, very convenient conversion factor. Okay, that is it for this lecture. Be sure, please, to contact me with your questions. Really, at any time, I'm not going to be mad. If I can't answer, I can't answer at that time, right? I'll try to get back to you as soon as possible. Yeah, that is it. Thank you for joining me for this lecture, whether you watched me faster or whether you watched me slower. Have a good one.